Hey everybody, good morning, good afternoon, or good evening, whenever it is that you're watching this. What will honestly turn out to be a wonderful piece of work. So I encourage you to enjoy it the best that you can, being as how this is probably one of the best things you're going to do all day. All right, so just from me to you, just being honest. A couple of things to just put up here on the calendar. PLC 1 quiz style format on Canvas. If you haven't checked it out already, go ahead and get a go on that. 3 tries, and we'll see how we do. And in general, that will be the PLC format, right? So this is the this is the doing of the 1 hour that is supposed to be done via class policy, because you're getting 5 units for this class. Homework 1 I've posted. Remember, that's going to be due Tuesday on February 10th, not this coming Tuesday the 3rd. It's the week after that. It contains reflection, which we are going to finish off today. It contains refraction, which we're going to talk about next week. Lab 1, we're going to get started on Friday. I'll post that up. We'll get that going. I am still tweaking a few things on it, and we'll see how we do. All right? Hopefully it's just going to be a fun time. Anyways, we're going to continue now. This is day 3 of me reviewing for the final for you. So hopefully this is going well. And by the time the final arrives, you'll have had all this 15 weeks worth of review under your belt. So cool. Let's get started. I think we finished off last time talking a little bit about the sign convention that we wanted to go through with mirrors and the establishment of the positive and negative side based on where the mirror was and the symmetry axis. So we'll go into a little bit more of that. And remember, last time I left you with a bit of a puzzler, that there was an approximation involved somewhere. And maybe we can track it down today and see what it looks like. So by way of picking up where we left off, okay, we have the plane mirror, the converging mirror, and the diverging mirror. So each of these, each of these we have drawn the ray diagrams for. And in fact, last time I went through and went ahead and did a little bit of math on one of the ray diagrams in particular, and that caused us to be able to come up with an equation which will mathematically describe a little bit more precisely than the ray diagrams do where the image is and what its size should be. Okay? And so hopefully that will, we'll have a little bit of practice with that today, and so hopefully that will be something that you can get familiar with. All right, so we've gotten the ray diagrams checked off for each one of these. We know for the curved mirrors that the rays that we choose, we have 3 kind of maybe call them principal rays, the 3 that we kind of concentrate on. Remember, you really only need 2 rays in order to figure out where the image is, and the 3rd one is kind of gravy on the wedding cake. So when you have these converging and diverging mirrors, really what you're doing is you're trying to establish, okay, where is the image, what size is it, what's its orientation, right? The 4 image questions. All right, so we've got our ray diagram, we've got our math representation. And the math representation looks like this, where the focal length, a bit of glare there. Let me just draw it. I'll write it a little bit lower so you can see it. The focal length is F. The object distance is DO, and the image distance is DI. Now, you may see many different representations for these variables. You may see S and S prime, or P and Q, or I and O, or something like that. That's a really tough one because I and O look like math numbers. But anyways, I think this is the way that I'm going to go ahead and do it. Just reminding you, this is the focal length of the mirror, object distance here, and image distance is the other one. Now remember, these distances are measured from what we call vertex of the mirror. Okay, it's the point where the symmetry axis touches the surface of the mirror, right? So at that point, we're measuring the focal length, we're measuring the object distance, we're measuring the image distance, whatever it is. Okay. As always, make sure your units are copacetic. Okay, if you're going to use centimeters for this, just use centimeters for everything. It's not a situation where, and by the way, I'm just going to put this out there as a general mentality because it's very likely that you have no idea how I do things, and you may have been trained to do things via a math or a chemistry way or some of these other lower subjects, that you have to change everything into meters. I'm not concerned about that. I just want consistency. If you're going to use centimeters here, just use centimeters everywhere. Millimeter, just use millimeters everywhere. It's totally fine. I'm not a stickler for units unless they don't match up, right? So you're going to start with the focal length in centimeters and you're going to tell me the object distance in meters. Now I've got a problem, okay? So just make everything consistent throughout it, all right? And that's going to be a theme throughout this class. That's not going to change, all right? I'm just going to, we'll come back to it at certain points. All right? What I'd like to do now is take a look at a couple of different, say, special cases for the application of this to these mirrors, all right? So let's take a look. How about we start with the easy one? Let's look at a plane mirror. Okay, a plane mirror. Let me go back one sec here real quick. Let's just remind you that the focal length is half the curvature, half the radius of the spherical mirror, where I said that F was equal to 1/2 R. And that tells you that the focal length equals 1/2 radius. Okay? Now, and that's a geometry property, and you can look through that and do some circle geometry on that, and you can convince yourself of that it's no big deal. Okay, so let's take a look at a plane mirror with these ideas in mind. Now, what would be the radius of a plane mirror? Well, would you say 0? Well, a radius of 0, that means it's kind of like a point. Would you say the radius is like infinity? I think I would probably go more that direction, because that means that your circle is so big that it looks almost flat when you zoom in on something, right? And by the way, that's true in general. Even if you have a regular sized circle, if you look at a small enough piece of it, it looks like a straight line, right? This is what differential calculus is all about. So what you do is you say, all right, if I've got an infinity radius, well, then I've got half. Obviously, my focal length is infinity divided by 2. And that's, again, not really a number. It's large, focal length of infinity. So that puts the focal length at infinity, which means you kill this side of the algebraic relationship. Okay, so for a plane mirror, what this boils down to is that, if you like, 1 over the image distance is negative 1 over the object distance, and that just implies to me that the the image distance is negative of the object distance. Okay? Therefore, you would expect that, and maybe this is something a little bit strange when you really start to think about it. The image that you see in the mirror, so if you look in your bathroom mirror, right, you're going to look in the bathroom mirror and you can say, ha, looking good today. The image you're seeing of yourself is as far behind the mirror as it is as you are in front of the mirror. Now, the reason I say maybe this appears strange to you is because many times people say the image is right on the mirror. I say, where's the image? And they would say it's right there. But that's not exactly right. That's not exactly true. What we're talking about is, where does it appear that the image is? In other words, take the mirror away and put a window there, right? Intellectually, we know that this thing is reflecting our image. But if we had no idea that that was going on, and instead we looked at this thing and just assumed that we could see through it, and all of a sudden there was this other person on the other side of it, and you'd go, oh, look at that person over there. That person would be the same distance behind as you are in front, according to what we have here. And I think you could say that tracks reasonably well, and we'll see why in just a minute. Because in just a minute, which is now, the magnification, which is what I want to talk about. The magnification is a very useful property. Now, we went through this a little bit yesterday. I didn't explicitly mention it, but you can imagine what this is. It's the number that quantifies how much larger the image is than the object. In other words, when we looked at the converging mirror array diagram yesterday, what I did was I arranged it so that we could look at the angles and the tangents and then the opposites and the adjacents, and we arranged them up into their ratio sides. Okay? And one of those ratios was the image height divided by the object height. Now, if you think about it, isn't that really what the magnification is? So, one of these, well, I should say both of those equations that we talked about yesterday that I ended up saying were equal were based around this ratio. Okay? So when we look at this and you say, okay, I'm interested in what this number is going to be, we already have some ways to represent what that, or say there's ways to represent how to calculate this. Okay? So, if you think back to the relationship that I came up with for array number 2, I think, we found out that when I did that, when I formed this ratio, it was the same thing as saying it's image distance over object distance, right? Because we had the triangle for the image, which involved the image height and the image distance, and so it was opposite over adjacent. So if we just multiplied those on the other side, then we would have gotten that. Okay, now, but here, I want to be careful. Let's think for a minute here about what's being represented when I say magnification. Okay, the magnification involving the height of the image. Okay, now hold on a sec. We put a coordinate system on the height of the image. We made a designation whereby we said, if the image is above the axis, we'll call that positive. If it's below, we'll call it negative, right? In other words, if it has the same orientation as the object, I'm kind of assuming the object is more or less always something like this. That's not always the case. So if the image is also this way, right? So I got my object here. If my image is also this way, well, then we're going to talk about a positive height for this and a positive height for this. So the magnification would be positive. But if we have the positive height object but a negative height image, then the magnification has to turn into a negative number. And what that tells us is that the image is actually opposite what the orientation of the object is. Okay? So we have to be a little careful with this. All right? Now, in fact, let's go back and make a quick table of the sign convention that we chose, because we need to modify this. So don't leave this yet. Don't leave this relationship yet. We need to come back to it. So let's just make a quick table whereby, okay, we have a mirror. I'll just choose a converging mirror here. If I have my object, then we already know to about there. Okay, so we know that that's the object distance. All right, so suppose now that it makes an image that's a real image we know is in front of the mirror. We called that positive. Okay, the real side of the mirror is positive image distance, therefore the virtual side over here is negative. All right. In addition to that, when we started with the object height here, we called this positive height. Now, if I form a real image with this mirror and the object as to where it is here, boom, 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 I'm not going to draw the rays in. I'm just going to say, all right, let's just suppose the image is here. Okay? Image distance is therefore right there. If that's the image distance, note it's on the real side, which makes it a positive number according to our sign convention. Right? This number is a positive number. The object distance is also a positive number. Therefore, we have a problem in the magnification as how it is defined right now. And the reason is that with a real image formed, both of these are positive numbers. But that's a positive and this is negative. So the overall left side is negative. Therefore, we have to introduce, in order to be copacetic with our sign convention, we have to introduce a negative sign into here. All right? So the magnification is really the negative in order to describe the fact that real images, while they are in positive image distance space, usually are inverted, which means negative image height. All right? So we have, because that's our sign convention. So we introduce this negative sign in order to define the magnification correctly. All right. Hopefully we're good with that. So let's just call that equal to the magnification, and we'll call that M. Okay? M. That's not mass. That's magnification. All righty? Now, if we take a look at this and apply it to the plane mirror, now what do we have? Well, if I know that the magnification is negative, these two things divided by each other, but the plane mirror already tells me that these two things are equal to each other, though one is negative of the other, what I'm going to get is that the magnification, if I can just do that right here, that the magnification of this is positive 1. Right? That is the thing that tells you that we might be on the right track here. Okay? That's the thing that tells you when you look in a plane mirror and you see yourself, you are seeing yourself exactly at the same size as you are. Your image is the same size as you. And that's telling you that, and by the way, this also tells you that it's upright, which also tracks with what you expect, yeah? So that's telling you, hey, I think we're on the right track with how we're looking at this, okay? So the image distance behind the mirror being the same as the object distance in front of the mirror causes the plane mirror to give a magnification of exactly how big you are, okay? And that's a +1 magnification. Upright and not magnified or minified, the exact same size. Okay? And that comes from this thing right here, which tells you the image distance is this, the image height is the same as the object height. Alrighty. Good times? Great times. Okay. Let's take a look at that as applied to the curved mirrors now. Since we have this all kind of set out, I'm going to get rid of this. Okay. So our new piece of math to that is adding this piece to it here, which is the magnification, as a ratio of the image and object distances. Okay. now I think let's take a look at applying both the distance equation and the magnification equation to the two curved mirrors. So let's pick a couple of interesting points, because as you know, were I to change the object distance, I would change the image distance. Okay? So let's pick a couple of interesting points. Let's just say, let's start with putting the object really, really, really far away. Okay, let's start with DO approaching infinity. If we look at the mirror distance equation, I'll just call it the mirror equation if that's okay. If we look at the mirror equation with this, what we're going to notice is now 1 over f is equal to 1 over infinity plus 1 over image distance. And so 1 over infinity being essentially 0, as d approaches 0, we're going to find that the image basically shimmies itself right onto the focal point as the object gets really far away. And this is a good sign. Okay? So as the image moves towards the focal point, so what this tells us is that the image approaches f. When the object distance approaches infinity, the image distance approaches f. Now, this is a good sign because remember that one of the tenets that we talked about was that parallel incoming rays that are coming into the mirror parallel with the axis, focus to the focal point, right? They leave through going to they leave via going through the focal point. How do rays become parallel? Well, we can manufacture that, but if we just take a curved mirror and I say, look, I want to find an object whose light rays are going to be about parallel by the time they hit this mirror, how far away does the object need to be? All right, well, this is kind of basic inverse square thinking. All right, so imagine that I have a point source of light here and it's radiating light out like this. Right? As this goes further and further and further away, I'm just going to draw parts of this radiating pattern at this point here, right? If I think of the parts just further and further and further away, look at the curvature, right? These things are slowly becoming more and more straight. Now, what is a wave? Well, a wave is really crests and troughs. And a ray is related to the wave by being in the direction perpendicular to the crests and troughs. Now, if I consider these things to be crests, that means the ray is traveling to the right, as I've drawn it here, but less and more so, right? It's becoming a little bit more concentrated. So if I look at the ray, which is going that way, it's always perpendicular to the crests, whereas if I look at the one here, right, it's becoming a little bit, right? So by the time I get here, these things are all kind of starting to move in the same direction, whereas if I look at them back over here, look at these ones are going that way, there's that one that's going this way, that one's going that way, that one's going that way. There's a lot more variation in the directionality. So if I'm really far away, I'm way over here, by the time that ray comes all the way over here, can you see that the ones that are kind of going up at an angle, they're missing me. The ones that I'm seeing are kind of concentrated in a small range of being essentially parallel. So the object distance being very far away implies that the rays, as they hit, after traveling and traveling and traveling, when they hit you, are essentially parallel. Think about the sun, right? This is a perfect example. The sun is about 100 million miles away, okay? And by the time the rays hit Earth, like how big is Earth when you think about the light that's coming off the sun? The sun is shooting stuff and it's just spitting garbage in every direction. But Earth is just this tiny little thing that's way over there. So by the time the rays get to us, they basically have no choice but to be essentially parallel, okay? All right, so that's what this is. And that means essentially the sun is considered infinitely far away, right? It's so big that even when you focus it, it doesn't go down to its mathematical point. All right, so if we do that, notice that when we do the image distance going to being the focal length and the object distance going off to be infinity, that when we do this, the consequence of the size of the image is that the magnification becomes negative focal length divided by infinity. And this I shouldn't say equal to, I should say approximately, or say it approaches this, right? In other words, it's approaching 0. And what it's telling you is that the image is getting smaller and smaller and smaller as it approaches the focal point. Mathematically, it would say it's going to end up as a point, but we never end up there mathematically because math only describes a perfect world, and we live in a actual physical world. And so nothing is going to actually behave to the all the way to the limit. Nothing's going to satisfy the exact limit. Okay. But we get the flavor of the behavior by looking at what happens as it approaches the limit. All right. Okay, so that's good. So we got we got what happens here as the image or the object approaches infinity and the image approaches the focal length. What happens when the object approaches the focal length? What happens if the object distance approaches f? If the object distance approaches f, well, what happens to the image distance? Well, look. If I have 1 over f here and I have essentially 1 over f here, then I can't add anything to it. So that means the image distance is approaching infinity. Okay, basically the opposite of what just happened here, as you might expect. Okay, there's a nice balance or a nice symmetry to it in that sense. In other words, as the object goes really far away, the image gets to the focal point. As I bring the object all the way to the focal point, the image takes off and goes all the way to infinity. Okay. Now you might ask, what's a useful operational definition of infinity in this case, right? Mathematical infinity makes no sense in the physical realm, right? So what's a good operational definition of infinity when we're talking about mirrors with actual focal lengths? Well, to be practical, you're talking about something that's going to be probably more than 10 focal lengths away, right? It's going to be something whereby you can kind of plug in numbers here and say, well, if the object is more than 10 focal lengths away, is that pretty much good enough to make the image distance near the focal length? Yeah, probably. So there's no meaning to actual infinity here. It's just a signifier that something's far away. Far away compared to what? Compared to f. Because f is the thing that characterizes the behavior of the mirror. Okay. Now, when we do that, notice what happens here. The magnification. Oops, I should probably say approaches again here. I'm a little lazy with the equals. Magnification is going to approach infinity divided by f, and that means it's approaching negative infinity. Right? So it's approaching something that's flipped over and very large. And I think you could expect that, right? In other words, if you think about a lighthouse, though not really a mirror sense. Oh, how about a telescope, right? A telescope, one of those big radio telescopes. What's happening is they're tracking signals from very far away, and those signals are impinging on the radio telescope and going to the focal point. Okay? You could imagine the exact opposite happening, right? If I put a light here, it's going to come, hit the telescope, and head on out, right? And it'll come out as a beam. Okay? So that's one way that you find these beams. If you ever think about the rotating police lights, or like on a forklift or something, often that's what they used to be, right? Is a light sitting here, and then around the light there's a little axis with a mirror on it that just goes like that. And what it does is it creates a beam that circles around. right? Or one of the rotating kind of warning lights or whatever you want to call them. Okay, so we've examined those two limits. One other one that I think is useful to look at is the situation where the object approaches the radius, the center point. Okay. Let's suppose that the object distance approaches 2f, right? This is the radius, or what I often refer to as the center point. In other words, the center point of the circle that is made by the compass, right? So you take your compass, you stick the point in one, and you go around like this, right? The center point, that's the center point that I'm talking about. So suppose that we take our curved mirror and we know what the radius is, and we put an object there. What happens? That's twice the focal point, right? Because we know the focal point's half the radius. So we're now putting an object at twice the focal length. When you do that, you transform this into that the focal length, right? I'm taking our mirror equation and I'm saying, okay, 1 over f is 1 over the object distance and 1 over the image distance. But can you see what the image distance must be in order to make this work out? In other words, I have 1 divided by a number equal to 1 divided by twice. In other words, half that number. So the image must be also the same, right? In this case, the image then is going to approach 2f also. Okay. This is the point where the object and the image are right next to each other. Now, I'm thinking of a converging mirror at this point, such that if I have my object way over here, and my mirror is here, as I bring my object in from infinity, right? Initially, the image is here at the focal point, and it's inverted. As I bring it in, the image goes slowly, and then they overlap right here, and then we find that as I bring the object closer, right, the image shoots off and goes further and further away as I bring the object closer to the focal point. All right. So the center point is actually the one in which the object and the image are right at the same point when you put the object there. All right. Okay. So a couple of interesting little offshoots and explorations of this. Let's go ahead and take a look at a few examples. I'll throw some numbers in at this point to try and give you a flavor of how to use the mirror equation and before we do that, I should talk about the magnification. Well, actually, I think maybe we'll do that as we go along. So let's talk about how to use the equations in concert with the ray diagram so that you can kind of understand the whole process as a problem-solving set of steps. Okay. All right. So let's start off with a situation here where I have a mirror and I know the object distance, which is usually fairly typical. You'd say, "Oh yeah, I know what the object distance is because I put the object there." Okay. And let's suppose we have a mirror whose focal length we know, and we're going to say, well, yeah, I can measure the focal length of the mirror. Okay, so let's do this. And we want to know where the image is going to end up. Okay, so we'll try and do this as a full set of steps here that's going to help inform your problem-solving abilities here. All right, so let's take an example. We've got a curved mirror, and right now I'm not telling you. Notice that I'm not telling you what is it diverging, converging? We don't know. It's just curved, right? Curved mirror with a focal length of, say, plus 12 centimeters. And I'm going to take an object and put it at plus 18 centimeters. Suppose I have a candle or something. why don't we start by describing what can we figure out from this? Okay? Sometimes you will encounter a statement, and you might say, well, what am I supposed to look at? Anytime you have information, what I'd like to instill as a mentality is find out what you can, right? Within the context of what we've talked about. Okay? So let's start with this, okay? I want to start by drawing a ray diagram. That's how we want to start these. But I don't know what kind of mirror I have, okay? I know it's a curved mirror. It's got a focal length. It's not a plane mirror. It's got a focal length of plus 12 centimeters. Now, I have to think back now. I have to track with what does this positive sign mean, okay? I have to make that copacetic with our sign convention. Remember now that when we talked about a mirror, we had a real side, we had a virtual side, and we said that our sign convention looked like this. All right? So if I'm saying that the focal length is positive, that means the focal length is on the real side of the mirror. Okay? The real side of the mirror is where the light is. That must mean that if I have rays coming in like this that are going to hit the mirror and the focal length is on that side, it has to be a converging mirror, right? Because the place where I would put my compass, the center of my compass, in order to draw this, right? I would have to put it here, and that's on the real side. That must tell me that the focal length, the focal point is also here in the real part. Now, if it was the other way, right, I would have my compass over here making this kind of mirror. That would be a diverging mirror, but that would give me the virtual focal point. That would literally mean the focal point is negative. Now, I think sometimes there's more connotation or more meaning that students want to imbue to words like virtual or negative. It means like it means less than zero. Does it mean literally less than zero? No, because what we're trying to do is describe a position. And in order to make measurements appropriately, we have to define a zero of position. So suppose I have a zero of position, it's right here. Well, if I'm over on this side, I'm on the negative side. My position is currently negative whatever, negative 4. Okay? Whereas if I move past 0 and I go here, well, now my position is positive 4. Okay? All right. That's just referencing a 0. It doesn't mean that something is literally less than 0, right? It's referencing where are you with respect to 0. So, and the same thing with the word virtual. Don't get too caught up in trying to say, does it virtual? Is it really there? Does it really exist? It's just on that side of the mirror, right? So this is what this is getting after. All right, so that's what the positive sign right here tells you. You have to, when you look at these, very often there are clues that are buried, and we have to be detectives and dig them up. All right, so there's a clue buried in the positive focal length, and that tells me right away it must be a converging mirror. All right, so what I'm going to do now is I'm going to draw my ray diagram, and I'm going to say, here's my converging mirror. I already know that my focal length is going to be, say, here. Okay, there's my focal length. And my object is outside the focal point. So if I say that's 12, so 18 is going to be half as much again, so it's about here. Okay, now let's start drawing the rays. Also, while you're drawing, have expectations in mind. We just went through a situation right over there where we talked about what happens when the object approaches 2f. Well, so does the image. Okay, is this object at 2f? Well, no, it's not. But, okay, where is it then? Well, the object, right, 2f would be 24, so it's within that. I would assume, therefore, that the image should be outside of 24 centimeters. The image should be, I'm expecting the image to be somewhere down here, right? Especially because it's a converging mirror. I'm going to get a real image with the object when it's outside the focal point. I'm going to get a real image. That means light's going to cross. If light's crossing from a converging mirror, that means it's underneath the axis. So I should be expecting something here that is a flipped over real image. Let's check out ray 1. Ray 1 comes in like so, leaves via the focal point like so. Ray 2 would go in here and then out there. I'm going to just use ray 3 because I really like using very obvious points to draw. So focal point's a great place to use for me. So I'm going to use the focal point. So I'm going to draw ray 3 instead of ray 2. Ray 3 is going to be this one right here that hits. Oh boy, this one's out here. There it is. We got it. I'm just going to draw the rest of that in, and then I'm going to say, here's my image right here. Okay, it's ticking a lot of boxes for me right now, right? I'm expecting it to be outside the 2F mark because the object was within the 2F mark. And notice that when you talk about the relationship of the object and the image distances, the object starts at infinity, moves in towards the focal point. The image starts at the focal point, moves away. They overlap at the 2F mark, and then remember that it goes like this. So think about how far has the object traveled and how far has the image traveled. So if I take the object from infinity all the way to 2F, the image has started at F and gone to 2F. In the amount of distance that this thing has covered infinity to 2F, this thing's traveled F to 2F. And therefore the opposite is true. When I take the object from from 2F towards F, the image goes from 2F to infinity. So it's really jamming. Okay, it's hauling the mail here. Okay, that means I would expect this to be well outside the 2F mark. And if I just look at it by estimation, the 2F mark is about here, and this is outside of it. Okay, good. It's also upside down, which we would expect because it's a converging mirror, and the object is outside the focal point. Okay. So if I take my 4 image questions, right now I've got a real image. Answer my 4 image questions. I've got real image. It's in front of the mirror. And the image distance is large compared to the object. Did I say that right? Yes, the image distance is large compared to the object distance. It's inverted, and it appears to be magnified. Okay, so these are the answers to my 4 questions. Those come right off the ray diagram. Now we start the mathematical analysis after drawing the ray diagram and after answering the 4 image questions. Now we start the math. Please don't jump straight to jamming numbers into equations. Okay? It's super important to me, and I hope that you can respect this. It's important to me that I get you to do these steps before doing all of your, because people, the issue is that people ascribe great meaning to the results of a calculation. I don't. I ascribe great meaning to this. Okay? So please, don't consider a number to be the solution. That's not the shining thing that you're looking for. I'm looking for this. I want to see this stuff. Okay? This is a huge part of your solution. Now we start the math representation. We know our 2 working equations because we've already derived them from the geometry of the situation, right? You could certainly go back and derive them again, and you can see them happening right in front of your face here, right? I've got an angle here and an angle here, and we can talk about these as similar triangles. I just got to sketch in ray 2. We can do the same thing, okay? So you can always go back and convince yourself, I'm looking at these angles, I'm looking at the tangents, and I'm getting the geometry of the situation worked out right. Okay, fine. In this case, we know the focal length, we know the object distance. I want to solve for the image distance. So the image distance is then the focal length minus the object distance. And at that point, I can plug in a few numbers and say that this is 1 over 12 minus 1 over 18. So if I think about, you can certainly do this on a calculator. I do feel like quick, sometimes mental math, but not always, but just like quick pen and paper math, or really pencil and paper math. Quick pencil and paper math is good for your soul, and it's good for your mentality, and good for keeping you sharp. So let's think about what we can do with this thing. This is basically the same thing. If I can do this here, yeah. This is basically the same thing as a half minus a third if I factor out a 1/6, right? So a half minus a third is really easy to deal with, right? Because all I got to do is turn them into something with a common denominator. That's way easier than turning this crap into a common denominator thing, right? So I could just say, oh, okay, easy enough, 3/6, 2/6. This is going to also be 1/6. So that's 1/6. That's 1/6. So this must be 1/36. Pro tip here, we're not done. Remember, this is 1 divided by the image distance. Therefore, the image distance is 36. I got to still flip that over, okay? The image distance is therefore positive 36 centimeters. Okay, positive, which tells us, yes, it's on that side of the mirror. It's far away, right? It's well outside the 2F point, which would have been 24. So this is, okay, this is kind of like checking some boxes, right? This is saying, okay, yeah, I think this is a good representation of what we needed. If I look at the magnification of it, now that I have the image distance, I can look at the magnification of it. Negative, and I'm going to take my positive 36 centimeters to the top here. Centimeters. I'm going to look at the object distance. The object distance is 12 on the positive end. That's positive 12, and that's positive 36. So we got something like this. I'm going to end up with, you can probably see, this is negative 3. Again, tracks reasonably well with what we came out with on the ray diagram. Would I say it's exactly 3 magnified? Well, if I was being precise about it, I would say that's not. That looks closer to 2. But remember, that's not what the ray diagram's point is. That's not what we're trying to get out of the ray diagram. All we're trying to get out of the ray diagram is, hey, do we think it's magnified? Do we think it's the same size? Do we think it's minified? That's all we're trying to get. This is not a quantitative diagram that you're going to do to scale. I mean, unless you really want to, go right ahead. But I'm just trying to get the flavor of what the image characteristics are, right? That's why I want to answer the 4 questions about the image based on my ray diagram before moving on to the math, because this really informs what am I looking for. Then I start getting these numbers. I go, oh yeah, look at this. That's magnified. Oh yeah, minus 3. That's inverted. Well, this is good. Okay. Now, minus 3 on the magnification. I want to take a minute to talk about what this means. The magnification is tricky. Well, it's tricky until it isn't, okay? That just means you've gotten used to it. The magnification gives you two pieces of information, not just one. It's two pieces of information. It tells you, essentially, by the algebraic sign, it tells you whether it's upright or inverted. Okay, it's going to tell you whether it's upright or inverted by the plus minus sign. So I look at this -3 and I go, oh yeah, it's flipped over. How do I know that? Because remember, the magnification is based on the ratio of the heights. Image height to object height. Remember, that's negative. That's positive. So this image height is negative. I would expect a negative magnification here. That tells me that the image is flipped over relative to the object. Okay? And it's got a value of 3. Well, a value of 1 is same size. In other words, no magnification. Right? A value of 1, like the plane mirror, had a value of +1. What does that tell us? It's upright and the exact same size. This is -3, which tells us it's flipped over and it's much bigger. Right? It's 3 times as large. So via the number, the absolute value, if you like to think of it that way, but the number tells you how much bigger, or if you like, how much scaled down it's going to be. Magnified or minified based on the magnitude, based on the size of the magnification. So I'll just put M in absolute value bars. It just tells you that if you look at just the number, right? If -3 absolute value is 3. If I look at just the number, that tells me, oh, it's much bigger. If this was 0.25, I'd go, oh, that's way smaller. It's 1/4 the height of the object, right? Okay, so the magnification gives you two pieces of information. Please be aware of that. In some sense, the image distance gives you a couple of pieces of information too, in the sense that if this is positive, it tells you whether it's behind or in front of the mirror, right? Based on our sign convention of real side positive, virtual side negative. Oh, right there. Mm-hmm. And it also gives you the sense of how much further away from the mirror is that from than the object is, or how much closer might it be. Okay, so maybe that's not that big of a deal. But point being, it tells you where and which side. Okay, so we've got that. I'm just going to reiterate, please, when solving problems, get in a picture, especially with this first one, picture 4 questions, then hit the math, okay? Please don't jump straight to doing this. Or if you do, leave yourself a big space before you do it, and then maybe you can just trick me into thinking, oh look, I did this later, when in fact you did this first and you went back and did that later. Okay, fine, but I want to see this, okay? Alrighty. Let's take another look at another example here. Let's take a look at another example here. Yeah. All right, what happens, let's do this one. What happens if I flip these two? What happens if I now make that? I say the focal length is 18 centimeters, and I've put the object at 12 centimeters. Has anything changed? I mean, probably not, right? They're the exact same number, Isn't it pretty much the same converging mirror? It's got a positive focal length. We know it's a converging mirror, 18, 12. It probably doesn't mean anything. It probably means we'll end up with pretty much the same thing. Before we jump to conclusions, maybe let's take a quick look. Physically, if I say that the focal length is positive 18, okay, yep, we're still on a mirror. This is not the same mirror as it was in the previous example where we did a positive 12. But it's still a converging mirror. We agree with that. But now the object placement is within the focal point. So that means that this drawing is not valid. The object needs to be in here. That turns out, as I think if you remember from last class, that turns out this is going to change the image completely. All right? So let's take a look at what's going to happen here. I'm going to leave that here. I'm going to move the focal point out a little bit, but I'm going to leave the object where it was. Well, just for the purpose of drawing. Okay. I'm going to say that the focal point, this is, now this thing is half this distance again, so the focal point's like somewhere out here. Okay, so this is now what our mirror and object situation looks like. We don't have this image here. But notice, we still have ray 1. Ray 1 is still valid, right? Remember, it doesn't matter where I slide that object along that axis, as long as I have ray 1 drawn, it still is doing, except it's not going through the focal point anymore. Oh, I moved the focal point. But it would have had I left the focal point there. Darn it. And just move the object in a little bit. Oh well, too bad. I gotta redraw it now. Okay, well, that's why I brought this in. So that I can get these, I can get these long rays drawn appropriately here. Okay, so here's ray 1 now. It would have been the same. Man, had a golden opportunity to not change anything. There's ray 1 now. I'm going to again examine ray 3 just because I like ray 3. So ray 3 ray 3 is going to be the one that apparently leaves the focal point and goes this way. Hits the mirror, it goes that way, and then comes away this side. Whoops, got that a little bit chunky. All right, comes away that way. Now notice this is the situation of the two diverging rays leaving the converging mirror. The top one is straight leaving. This one's angled downwards. We have diverging rays. Ding, 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 ding. Flag should be going off in your head going, hey, I got to trace those back. My eye is going to see these things and my brain's going to go, where'd they come from? So we have to find out where they came from. Okay, that means I'm going to take this one back like that. I'm going to take this one about like that maybe. I don't know. I may have curved that one up a little bit, but that's what happens when you freehand. Yep, I did. Should be going a little bit more further out. Anyways, we're going to go here. Okay, so the image is now here. Just by changing those two numbers around, we have completely changed the flavor of this problem. Okay. All right, now that we're out here, 4 image questions. What kind of image is it? By now, I hope that you're getting used to recognizing this. Okay? This is a virtual image. It is upright. It is also apparently magnified, and we would say it's behind the mirror. It's in virtual space. And it seems to be, I don't know, it seems to be a bit bigger than the object distance. I mean, I should have gone a little further out, so it would have pushed it that way a little bit. So I would say it's farther away from the mirror than the object is. Let's check that with the math. Now that we've done the ray diagram, answered the 4 questions, let's check and see what we have. This is all still true. This is also all still true, but now I have to fool around with the numbers a bit. Okay? So now I'm going to take these and say, all right, I've got 1 over f, which is 1 over 12, minus 1 over 18. Nope, I did that wrong. This is 1 over 18. Sorry, 1 over 18 minus 1 over 12. Okay, there we go. If you are familiar with numbers, which I hope that you are, you'll probably notice that this is going to turn into a negative number. This 1 over 18 is less than 1 over 12. So I'm going to I'm going to end up with a negative number here, right? But I'm going to do the same. I'm going to play the same game as I did before. I'm going to factor out a 1/6, and I'm going to notice that this is now 1/3 minus 1/2. A third minus a half, right? That's like a third this way, but minus a half is way back here. So this is negative 1/6. And therefore, the image distance turns into negative 36, which is kind of fun. Because numerically, it comes out almost identical. But physically, this is a completely different situation. Completely different. It has, other than the mirror being converging, there's nothing that's the same about the previous example, right? This is a completely different situation. The image is totally different. But funnily enough, the numbers work out the same, or almost the same. So don't get fooled by this, okay? Especially if you're just jamming numbers into equations and you're going like boom, 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 and you're firing darts, and you're going, look, it's 36, that's 36, this is the same problem. No. Be careful, okay? Please think through what we're doing here. When I get to the magnification now, I'm going to change this number to minus 36 on the top and a positive 18 on the bottom. Okay. Notice that this number, which is negative, is now canceling with the negative that's inherent in the definition of the magnification. This means that my magnification now is not going to be negative, nor is it going to be 3, but it is going to be positive, and it is going to be 2. All right? Does that match what we did here? Let's check. First of all, the image distance being negative, that tells us, look, it's behind the mirror. When it's behind the mirror, we have a virtual image. So these two here are kind of connected, right? Especially for a single component system like one mirror by itself. If I have the image behind the mirror, that is definitely a virtual image if we're talking about a single mirror. So this thing right here is telling us, yeah, that's what we're seeing mathematically, and so this is tracking with our ray diagram. The positive 2 on the magnification here. Remember, 2 more pieces of information. Number 1, the positive tells us it's upright. Okay? There it is, upright. Plus 2, I can say, yeah, that's definitely magnified. I don't know if I'd give it a plus 2. It's probably close-ish. So yeah, it's magnified. Good. Our math works out with what our intuition is telling us. And ultimately, that type of thing is what I want to work towards with you. Does your math match what your intuition is telling you. That means you have to build your intuition. Okay? And that's what these things are all about, is building your intuition. You do a couple of these and you start to notice patterns, right? Especially when you answer the 4 questions. You see that there are links. Oh, it's behind the mirror. It's going to be a virtual image. Or vice versa. Oh, I think this is a virtual image. I bet that's going to be behind the mirror. Okay? And you can see just by looking at the problem, hey, look, the object is within the focal point. That's going to give me a virtual image. Let's just check and make sure that's happening. Boom, boom, boom. There's your intuition. It's happening right in front of you, right here. Then, does the math check with what you think is happening? And ultimately, that sequence, okay, in terms of sequencing and guidelines, that set of sequenced thinking is a great guideline as to how physicists do things. We don't do things for the math. We make the math do the things we want them to do, because this is what we're thinking, and that had better match what we're thinking. And if it doesn't, either it did something wrong or we did something wrong, right? And let's admit it. We're physicists. We don't want to admit that we're doing something wrong. We don't want to, but we have to. That's like 95% of the time we're probably doing something wrong. All right? So believe me, it's just a little matter of getting experience here. Okay? Work on building your intuition. Don't just rely on what the math is telling you. Okay? Please. Okay, let's do, I think we got time for one more example here. So let's move to the negative. Let's do a couple of different numbers. Let's do different things here. Let's do this. Let's move to a negative focal length. I'm going to say that the focal length, say, is negative 10 centimeters, and I put the object at 8 centimeters in front of the mirror. Okay. At this point, if you are paying reasonable attention, you have probably already figured out what this example is going to be. Since I have done one of those and one of those, it is mainly concentrating on getting the other one. Okay, all right, good. Let's just make sure that it is where we're thinking it is. It's a curved mirror, and now my focal length is negative. Okay, remember what that's telling you? The focal point is in the virtual side. The center point is on the virtual side. The virtual side's over there. The real side's over here. This is a diverging mirror. The focal point is, say, here. Well, sure, why not? Here's F. That's on the negative side of the mirror, right? The object is going to be on the positive side of the mirror. If it wasn't, what are we even doing here? Okay, the object's going to be over here. The image formed. Where is it going to be? What are we looking at? All right. So let's take a look. That's a 10 centimeters. So I'm going to put it in right about here. Let's say that our object is right there. Oh, to make it a bit bigger than that. Okay, object is right here, and we're going to do the two rays again, and see what do they bring us. Okay, ray number 1. Okay, and it comes away as if it left through the focal point. Like so. There's ray 1. With the dashed line, I already have a very good understanding of where I expect the image to be. It's got to be within this little triangle right here, right? That's the boundaries of ray 1. Okay, it's not going to be outside of that. Ray 2, ray 3, whatever you like. I guess for a change of pace, we could do ray 2 here. Let's go like this for ray 2. Maybe something like this for rate 2. I trace this one back. Right there. There's the image. Let's get some 4 questions answered about this image. This image is virtual. Behind the mirror. Upright. Minified. Okay, this is, by my diagram, it's looking smaller. Not much, but it's looking smaller. Okay? All right, let's see if the math matches our intuition here. I should be finding something in which my image distance is negative. I should be finding something in which the magnification is positive, but less than 1. Minified. Okay? Let's try it and see what happens. I'm just going to jump to this part, which is solving for the image distance. There we go, focal minus object. And therefore, I'm going to put in minus 10. Yes, keep the negative sign. You have to have the minus sign in here. Minus 1 over 8. Okay, this is not going to be a tasty fraction, but notice that it's definitely going to be a negative number. Negative minus positive. Okay, negative and negative. So it's just getting bigger on the negative side. I guess we're going to 40 for this stinker. I could go 2, which gives me 4 and 5. 4th and a 5th. Okay, that might work. We could try that. If I factor out a negative 1 over 2, that's going to give me 1/5 plus 1/4. Is that true? If I factor out a 2, that's going to give me a 5th and a 4th, and that negative is there. Okay. A 5th plus 4th, this is 0.2 and this is 0.25, so this turns out to be 0.45 multiplied by 2, which is 0.9. No, that's wrong. That's multiplied by 0.5, so it's 0.22. Flip that over. And what is that? I don't know that number off the top of my head. 5th and a 4th. Oh well. We can go back to doing it this way then, I guess. Or we can do 4/20 and 5/20, which is 9/20, 9/40. Well, not spectacular. Let's see if I can just pop a calculator on here and see what we can do. Okay, turns into, I get that the image distance is negative 4.4 centimeters. 40 ninths. I guess that makes sense. I would have said it's a 0.1, so multiplied by 4. Fair enough. A little above 4, right? It was almost 4 divided by 10. I just missed it by that much. Let's take a look at the magnification. The magnification is now negative image distance over object distance, and that means our image distance is negative. So we keep that minus sign in there. We divide by the object distance, which is 8. Again, our minus cancels with our minus. Oh, by the way, I meant to say this, but in the magnification has no units. Notice it's just centimeters divided by centimeters. Okay, so this is just a number, which is appropriate because it's a ratio of heights. So this turns into positive something about half. I'm going to go 0.5, maybe about 0.55. It's going to be 0.555, 0.56 probably. Okay, but check it out. It's positive. That's upright. It is less than 1 in magnitude. Minified, right? Half the size, a little over half the size. Okay, Alrighty. Very important to keep track of your negative signs. Okay? Keep track of your negative signs and use them. Okay? That focal point should be negative. If it's given as negative and this is a diverging mirror, or if I just say, hey, there's a diverging mirror with a focal length of 10 centimeters, then you need to know to put that minus in there. Okay? And that needs to show up in here, because otherwise we're doing a different problem. Okay? And then the interpretation of the minus signs, right? Minus sign in here as well. Interpretation of the minus signs, or lack thereof, right? Minus sign means behind the mirror. This looks good. Behind the mirror, it's 4, I don't know, the distance didn't really, I mean, it's less, but it's not that big of a deal. It's negative, which is behind the mirror, indicating it's virtual. Positive, magnification, upright, less than 1, minified. Okay? So, fortunately, these are all kind of fitting together. And what my goal is for you is to be able to see, how does this tell you about this, which then tells you how to interpret these things, right? Once you answer these questions, you already kind of know what you're looking for here. And ultimately, that just makes your problem-solving process easier, all right? Because you should try, I'm just telling you this as a guideline. This is, in fact, a passed-down mentality for physicists, which is don't do math, don't try to solve any problem until you already have an idea what the answer is. Okay? If you are not familiar with who John Archibald Wheeler was, then that was his quote and that was his mentality, and the greatness of that idea and the greatness of him are kind of portrayed in that saying. Don't start anything until you already kind of know where you're going. All right? We know where we're going. We already know what we're looking for. We know what our numbers should turn out to be. Okay? And these are okay. Now, could I tell you the numbers are exactly right? What if this turned out to be 0.7? Well, I wouldn't be able to tell you if that was right or not just based on my intuition about these, but hey, it still works. So, is it correct? Sure, it works with my intuition. You just got to check to make sure the value is working out for you. All right. Good. Okay. So I think that's probably going to just about wrap it up for today, as I'm noticing we're just about out of time. So let's go ahead and say that we are mainly done with reflection. We will return to it briefly because we're going to next week discover a different perspective of thinking. Okay, and so I want to return to reflection to provide some context for that method of thinking. Next week we're going to start with refraction, and that means we're going to talk about how light travels as it changes from one medium into another medium, like water into air or air into glass or something like that. Okay. Lab on Friday and a homework for a week on Tuesday. PLC for Friday. Friday, that's going to be the midnight. That's 11:59. Okay. And other than that, I will see you back in class next Tuesday. Remember that your lab write-up is going to be due before we start again on Tuesday. Okay? So keep that in mind, that assignments, keep on top of those assignments, okay? Make sure that you're turning stuff in. Other than that, from the class instructor, I'll see you tomorrow as the lab instructor, but from the class instructor, I hope you have a great weekend, and I will talk to you next week. Alrighty? Ciao, folks. See you later.